Hi there science students, we're going to continue our study of moles, and in this video we're going to introduce a second equation relating to moles, this one here, that says that little n is equal to lowercase m over uppercase M. So in this case, the lowercase n still remains or still represents the number of moles, as in the previous equation that we studied. The lowercase m is the mass in grams of a substance, and the capital M is the molecular mass. So you can see that rather than relating the number of particles and Avogadro's number, we're relating the mass of a substance. And it's through this equation that we start to see the true genius and the magic of this discovery of moles. Up until this point, we've understood that a mole of a substance has 6.02 by 10 to the 23 atoms or particles in it, and that big number, and yeah, that's interesting. I wonder where that number came from. Now, with the study of this equation, we're going to see just how useful moles are. But first, we've got a few things to work out, like what is molecular mass. That's important. Also, we need to understand the link from this new equation to the one we were studying earlier, which said that number of moles was equal to the number of particles of that substance divided by Avogadro's number. That's one form of the equation. And of course, the common link between these two, you might see, is that they both have the number of moles in the equation. So we can link these equations somehow. And we will do that as we go along. But first, let's just become familiar with the new equation and how that works. So you might want to pause the video at this stage and fill in this triangle that helps to rearrange it, and try and make the lowercase m and capital M the subject of the equation, and then I'll proceed from there. So go ahead and pause. Okay, so let's see. Little n down here, m up here, and big M there. Now, if we want to make little m the subject of the equation, that would mean that we take the number of moles and multiply it by the molecular mass, and that tells us the total mass of a substance. The molecular mass is equal to the mass of the substance that you have divided by the number of moles of that substance. Okay, both very important equations that you'll need to recall later on at some stage. So the big thing now is, well, we understand that if we've got a certain mass of something, we've got a certain amount of it, and we are becoming familiar with what number of moles are. That tells us how many particles we have of a substance. But what is the relative molecular mass, or as I've called it here, just molecular mass? Now, we're actually familiar with this. We have looked at this before. It's the same as calculating, say, the relative atomic mass. Now, if you look to the periodic table, you might remember that the relative atomic mass, or I'll call it here RAM, of carbon is about 12.01 atomic mass units. So that's for carbon. Now, the relative atomic mass for, say, hydrogen is about 1.008 atomic mass units. Okay, so if we look to the periodic table, that's where we find those numbers, say, in a test type situation. Now, the reason I picked out carbon and hydrogen there in particular is because here we have the chemical methane, that hydrocarbon, and they have carbon and hydrogen. So to get the molecular mass of methane, we need to know the atomic mass of carbon and hydrogen. Now, just for simplicity, I'm going to round those numbers to the nearest whole number, pardon me, which usually works fine. Okay, so the relative molecular mass of methane. So how many carbon atoms in a methane molecule? Well, that's 1, and each of those is 12 atomic mass units, plus how many hydrogens? There are 4, and each of those is 1. So if we add that all up, of course, we get 16. Okay, so that is the relative molecular mass of methane. Now, the units for this are 16 grams per mole. Okay, now that's an unusual or a new unit perhaps for you. So what that's telling us is that in each mole of methane, there are 16 grams. Okay, now this will become more familiar to you as we go along. The molar mass of methane. Well, look, that's pretty much the same thing, except here we just need to say 16 grams because we're asking the molar mass. How much is does 1 mole of methane weigh? 16 grams. So the mass of 1 mole of methane is 16 grams. Now let's say we have more than 1 mole of methane. Let's say we have 3.2 moles of methane. Well, we take 16 and multiply it by 3.2. You can see here the mass, we're just using this equation here, aren't we? M equals the number of moles times the molecular mass. I've got that the other way around. Normally we'd be like the number of moles first, you judging by that equation. So 3.2 times 16. I haven't done that calculation yet. 3.2 by 16 gives us 51.2 grams. So 51.2 grams. 3.2 moles of methane weighs 51.2 grams. Righto. Now, armed with that knowledge, let's look at these ones here. You might feel like you can pause the video at this stage and have a go at them on your own. So if you'd like to do that, I'll give you an opportunity, then I'll have a go at it. Right, so 1 mole of carbon. Once again, for simplicity's sake, I will just round to the nearest whole numbers on these. So if they're saying 12.01 on the periodic table, I'll just go to 12. Okay, 1 mole of carbon weighs, well, mass is equal to number of moles times the molecular mass. So we've got 1 mole by 12 for the molecular mass of carbon, 12 grams. 1 mole of carbon dioxide. Okay, so carbon dioxide, CO2. Now we can use this notation here. I'm going to go capital M, molecular mass of CO2 is equal to, okay, so we've got 1 lot of carbon in this molecule plus 2 lots of oxygen. Now oxygen, have a quick look in the periodic table if you haven't already. What is the relative atomic mass of oxygen? It is, of course, 16. So 12 plus 32 gives 44 grams per mole. Of course, that is the mass because we've only got 1 mole of this carbon dioxide. So using the equation above, number of moles times molecular mass, 1 mole by 44 grams. Okay, if it's 2 moles, well, we're going to double that. The mass is equal to 2 times 44, which is 88 grams. 0.3 moles, okay. Mass equals 0.3 times 44. Okay, what does that give us? I'll try and do this without a calculator. 4 by 0.3 is 1.2, and 40 by 0.3 is 12. So does that give us 13.2 grams? You better check that one for me. Okay guys, so go ahead and check the questions in the description for the video. Those questions will be in the yellow booklet on those pages that are described. And let's become familiar with this second equation relating to moles.